And so again, we call them positive counting numbers. And so specifically, all right, we've got 0, 1, 2, 3, so on. Those are our whole numbers. Again, intuitive, we generally know those just by looking at them. Now, integers, again, a lot of people had very strong starts to this definition. Nearly every paper I looked at mentioned we have negative numbers going on, which is good. However, what I want us to be careful of is it's not just the negatives. And so integers are positive and negative whole numbers. Positive and negative whole numbers. So anything that counts as a whole number, you can take that. If you put a negative sign in front of it, it is now an integer. Alternatively, any whole number can also be called an integer. So we could have -2, -1, 0, 1, 2, again, so on. And so now we have rational numbers. Now, rational number gets into a more specific definition here. And so integers, awesome, easy, clean, positive and negative whole numbers. Rational numbers are positive and negative numbers that can be represented, again, just abbreviating that as rep, as fractions. Positive and negative numbers that can be represented as fractions. As you continue through your math career, the idea of rational and the term of rational really starts to become synonymous with fractions. And so we'll see that when we talk about rational functions, rational numbers, rational values. Another way that we think of them are repeating or terminating decimals. Repeating or terminating decimals. Now, repeating decimals we've seen before, right? We put a bar over that last number, like 0.33333333. You just put the bar over it, and you know that goes on forever. Terminating simply means that it terminates, right? It ends. And so examples are going to end up being 1/3. You could have 2/5. We could have, I'll actually use that one, 0.333, right, where that goes on forever. Or we could even have something like 0.125. All of those are considered rational. Now, this 0.33333 forever, raise your hand, do you actually know what this is as a fraction? This is actually 1/3. And so if you were to change 1/3 into a decimal, that's what it looks like. Yes, it goes on forever, but again, it can be expressed or represented as a fraction. 0.125, same thing. You can represent that as a fraction. That's technically 1/8 as a decimal. All right, and so now we shift slightly away from what I'll argue is like the bigger family groups, and we look at prime numbers and composite numbers. Now, this is from the Do Now. A prime number is a number that is only divisible by 1 and itself. You can only divide these numbers by 1 and themselves. Prime numbers are incredibly useful, especially thinking about the field of cryptography and cybersecurity. A lot of random numbers and like random password generation has to do with prime numbers and using really, really big prime numbers. And so some examples, which are not huge numbers: 1, that's prime; 2, 3, 11, 13, 17, could go on. That's not necessarily all of them, right? There's a few that I skipped there. However, all of these numbers are divisible by only 1 and themselves. 2 has a special place in this list. 2 is the only even prime number. Now, that really brings us to composite. Whole numbers are either composite or they are prime. They are never both, and they are never neither. And so composite numbers are just any number with more than one factor pair. Right? In other words, there's just multiple sets of numbers that you can multiply to get there. 8, for example, is composite. 8 has 1 and 8, but it also has 2 and 4. Another example. We'll actually just do 1 here. 12. We have 1 and 12. We have 2 and 6. And we have 3 and 4. Right? That's 1, 2, 3 different factor pairs that make up that number. Next page. Go grab it. And so again, a number is either prime or composite. It is not both. It is not neither. Now, with this, there is one small addition we're going to make. It's tiny. It comes up on the exit ticket. It's technically in the infographic that we saw, but not necessarily a group that we use super often. And that is natural numbers. Natural numbers are simply whole numbers without 0. That's all. Natural numbers are just whole numbers without 0. And so, whereas whole numbers are 0, 1, 2, 3, 4, 5 forever, natural numbers are just 1, 2, 3, 4, 5 forever. Once you've got this one, flip your notes, please, so that I can see. Thank you. We're there. We're there. Thank you. Still have some writing. Take about 10 more seconds. Try and get this last one. All right, so on the back, example 1. Which of the following are irrational numbers? Awesome. Did we define irrational? No, right? We talked about rational. Well, irrational is, much as prime and composite are paired together, rational and irrational end up getting paired together. However, we will stamp what irrational fully means. And so just slightly below it, for a number to be irrational, it means, or I guess irrational numbers are any real number that can't. That's the really important part. Can't be represented as a fraction. And so these are non-repeating, and non-terminating decimals. Any real number that can't be represented as a fraction, non-repeating, and non-terminating decimals. Now, we've actually seen already an example of this, right? On the do now, we saw pi. Pi is considered irrational. Pi as a decimal, right? 3.14159, but then it has digits that go on forever. Those digits literally never stop. If you were to list out all the digits of pi, you would be there, well, frankly, until you weren't, because that would be the only thing you did for the rest of your life. Now, there are some other ones that we will see shortly. And so, let's re-look at the problem then, right? Because if I want to know which of these are irrational, well, process of elimination is truly going to be our friend here. And so, let's look at A. Okay, the square root of 4. Well, let's see if we can do this. Raise your hand. What is the square root of 4? One more. 2. Why? One more, keep going. 2 times 2 is 4. Alright? And so what that means is, well, wait a second. The square root of 4 is actually just a whole number. And here, I'll erase this and make this a little bit bigger. It's actually just a whole number. And so if the square root of 4 is a whole number, well then, there's actually no way that it's irrational. Whole numbers are definitely rational. Alright, square root of 10. Let's see, raise your hand. What number times itself gets me to 10? Antoine? 5? Careful. What's 5 times 5? 25. If we're adding, 5 would get us there. If we're adding, 5 would get us there. But here, we have to multiply. And so, again, we can sort of run through our options, right? We know 3 times 3 is 9. We saw that on the do now. But then 4 times 4, well, raise your hand. What is 4 times 4?
8.
Raise your hand. What is 4 times 4? Sage. 16. I'm going to name this one last time. I don't want shout-outs. If I say raise your hand, raise your hand. It's 16. Sage, thank you. And so, again, we have this awkward space where, like, we've gone from 9 to 16. We've skipped 10, which means that the square root of 10 is, it's actually just got to stay as a square root of 10. Because it does not have a square root, that is a whole number, is the way I'll preface that. That is irrational. Now, on C, pi. We already named that pi was irrational. I'm here to restamp. The fact that there's a 2 in front of it does not change that. And so C is also irrational. Now, 1/3, well, that is a fraction, so it definitely can be a fraction. And so D is out. And again, please raise your hand. What is the square root of 36? All right. 6. And so again, that's actually just a whole number. And so E is out. And so we have B and C as our irrational values. Now, on example 2, just on the other side, we're really just looking to stamp Y, right? Y is root 10 irrational when 1/3 isn't. And this comes down to what we've already really mentioned, repeating decimals versus non-repeating decimals. And so 1/3, right, we name this, is actually 0.3333 forever. However, the square root of 10, if you were to put this in a calculator, you get 3.162277660, and then it keeps going. There is no discernible pattern there when we look at the square root of 10. And so as far as, well then, y, 1/3 repeats. as a decimal. There we go. Where the square root of 10 does not. One-third repeats as a decimal, where square root of 10 does not. Again, when we think of irrational versus rational, it's truly, is there a pattern? If they're going to go on forever, there needs to be a pattern. They need to repeat. The square root of 10 does not do that.